Modeling with sine and cosine. The sine and cosine functions are so valuable because they can be used to model systems that are cyclical in nature. If an object moves in a circle at a constant speed, we call it uniform circular motion. Modeling the height of a passenger on a rotating Ferris wheel versus time is one example. There's another category called simple harmonic motion that involves the sine or cosine function. A vibrating spring mass system that oscillates up and down the same distance over the same time interval is an example of this. Here's another example of simple harmonic motion, an ideal pendulum that swings back and forth the same distance over the same time interval is modeled using either the sine or cosine function. Here's one more example of simple harmonic motion. An engine piston moves up and down in a cylinder the same distance each cycle. Provided the cycle is at a constant speed, either a sine or cosine function can model the piston motion. Let's compare the motions that are modeled with either the sine or cosine function. The red ball is modeling uniform circular motion. The blue ball is modeling simple harmonic motion. The Earth is a spinning sphere that rotates on its axis once every 24 hours. Because of this, there are numerous applications of sine and cosine functions. The angle of the sun above the horizon during daylight hours is one example. Periods are measured in units of time. Time is measured in seconds, minutes, days, weeks, months, or years. Choosing which time unit to use depends on the context of the problem. If a particle moves around a circle n times in t time units, the period will be given by t equals t over n. For example, a Ferris wheel makes 4 complete revolutions in 600 seconds. What's the period? The period is t equals t over n, which is 600 over 4, or 150 seconds per revolution. The number of times a particle moves around a circle in a given amount of time is called the frequency. The symbol for frequency is f. Frequencies are measured in units of revolutions per unit time. We will often use 1 over seconds, or seconds to the negative 1 power. Another name for seconds to the negative 1 is hertz, or Hz. Frequency can also be measured in revolutions per minute, or RPM. If a particle goes around a circle n times in t time units, its frequency is given by f equals n over t. For example, a Ferris wheel makes 4 complete revolutions in 600 seconds. What is the frequency? The frequency is f equals n over t, which is 4 over 600, or 1 over 150 hertz. Do you see the relationship between the period and frequency of an object's rotation? Write a formula that relates t to f without including n. Write a formula that relates f to t without including n. As you can see, period and frequency are reciprocals. The period equals 1 over the frequency, or you could write the frequency equals 1 over the period. Imagine a pendulum that swings as shown. Let the end of the pendulum be all the way to the right, where x equals 1, at time t equals 0. The next time the pendulum is all the way to the right is at t equals 2. So let's sketch that below. It starts out at time equals 0, x is at 1. So it starts out like this, and then goes like this, and then we have there. So at time equals 2, we're back at our value of 1. A displacement to the right of the equilibrium position x equals 0 is called a positive displacement, and a displacement to the left is a negative displacement. Using this reference frame, the equilibrium position is regarded as the 0 position. The position versus time plot is modeled by cosine. The position of the pendulum bob actually measured along the arc relative to its rest position is a function of cosine versus time. In this example, the period is 2 seconds. Let the end of the pendulum be all the way to the right where x equals 1 at time 0, so that's here. The next time the pendulum's all the way to the right is at t equals 2. So here we have the graph of this motion. What is the period? What is the frequency? What is the amplitude or displacement? The period is 2 seconds because that's how long it takes for the motion to start over again. What's the frequency? Well, that's the reciprocal of the period. So the frequency is 0.5 hertz. And what is the amplitude? The amplitude is 1. And that's the distance between the equilibrium position at 0 and the maximum. It's also the distance between the equilibrium and the minimum. A vibrating spring mass system's motion is sinusoidal. The mass at the end of the spring moves up and down along a vertical axis so that its position satisfies y is greater than or equal to -20 and less than or equal to -10. Let's imagine that at time t equals 0, the center of the mass is at its equilibrium position where y equals -15 centimeters and is moving upwards, arriving at the maximum position for the first time at t equals 0.1 seconds. What is the period? What is the frequency? And what is the amplitude? All right, let's draw out what this looks like. So we have our x-axis, but the midline that we're dealing with is below the x-axis, so it's down here somewhere. I'm going to elongate this. All right, so this midline is at -15, and the maximum is at -10, and the minimum is at -20. At the maximum position is at t equals 0.1 seconds. So this is 0.1, this is the maximum. So it goes like this, and then like this. So this point here would be at 0.2, this point is at 0.3, and that point is at 0.4 seconds. So the period is 0.4 seconds because that's how long it takes for the cycle to repeat. The frequency is 2.5 hertz because 1 over 0.4 equals 2.5. These are reciprocals. The amplitude is 5 centimeters because that's the distance between this point and the midline. -10 to -15, the difference there, the displacement is 5 centimeters. So the answer is 5 centimeters. Let's draw a graph of several cycles of this motion. So we have our x and y axes. We have our midline. And now I'm going to label our points. So we have -10, -20, and the midline is at -15. We're going to do several cycles, and the period's 0.4. So we have 1, 2, 3, 4. That's 0.4. 1, 2, 3, 4. That's 0.8. 1, 2, 3, 4. That's 1.2 seconds. All right, and so we have our maximum at 0.1. Then we hit the midline. Then our minimum at 0.3, and then back to the midline at 0.4. Here we have our maximum, midline, minimum at 0.7, and then back to our midline at 0.8, and then maximum at 0.9, midline at 1, minimum at 1.1, and then back to the midline. So our graph looks like this. And this is 3 cycles.